So welcome back. So last time we discussed, continue to discuss PID and prime ideals and maximal ideals, and irreducible elements and prime elements and their relations. So for example, in an integral domain, every prime is irreducible, but in a PID, every irreducible is prime. We proved that, and then, in fact, we saw that every irreducible generates a maximal ideal in a PID, and using that, we considered the polynomial in Fx. F is a field, and then irreducible element generated a maximal ideal. Then you show how it gave rise to field extensions, and this field extension was a finite dimensional vector space of degree equal to vector space dimension over F, Fx over polynomial, reducible polynomial is a vector space over the field f of dimension degree of that polynomial, reducible polynomial. Then we discuss the concept of associates. The two elements are associated if they differ by a unit. And then we saw examples of integral domain where irreducibles are not prime. And also we showed that in a PID, every non-zero prime ideal is maximal. And then using that, we classified maximal ideals in the ring Rx and Cx, where Rx maximal ideal can be quadratic polynomial, Cx every maximal ideal is given by linear polynomial. That is due to the fact that maximal ideal generally corresponds to reducible polynomials, and C is algebraically closed, so-called fundamental theorem of algebra, that every polynomial in Cx has a root in Cx. So next, as I said, we'll discuss UFD so today we discuss UFD or unique factorization domain and unique factorization domain. And so let us start with the definition. So let A be an integral domain, and then we'll see examples. Then A is called an unique factorization domain, or UFD in short. If basically unique factorization of an element into irreducible hold over there. So more precisely what it means, if every non-zero non-unit element x in A can be written as a product of irreducibles. Okay, so every non-zero non-unit element x, you take any non-zero and non-unit element x, then x can be written as a product of irreducible elements. So product, of course, means finite product. That is, so if you write in terms of mathematical expression, so let's say x in A, x is a non-zero, and x is not a unit in A, then x can be written as x equal to q1, q2, qn, where this qi is, these are irreducible elements, so irreducibles in A, and that is the first one. It can be factored into irreducibles, and second is equally important, that this factorization, that this factorization is unique. So second is this decomposition is unique. And what does it mean? So if you have another decomposition as x equal to p1 into p2 into pr, is another expression of x, okay, where these pi's are where pi's are irreducibles. Pi's are irreducibles in A, then r equal to n. Okay, so first of all, r equal to n. So the number of irreducible is same, and moreover, up to permutation py or qi are essentially the same. So and pi equal to Wi times Qi, where so up to, so you have P1 P2 Pn now, and Q1 Q2 Qn, R is equal to n, and Pi's or Qi's are same. So for some units, so they only differ by unit, so that is their associates, right? So that is Pi's and Qi's are associates. Pi's and Qi's. So Pi's and Qi's are associates. Okay, are associates in A. So both of them differ by elements in A. Okay, so every non-zero, so in summary, every non-zero non-unit element can be written as a product of irreducible, and this product is unique. So if you write it in any other way, then they can only differ by unit. See, so in this expression, up to unit, you cannot say anything. So for example, okay, so let's talk an example. Maybe it will be a bit more clear. So example, as you know, so example, Z is a UFD. Z is a T. This is called, if you remember, the fundamental. So last class I talked about fundamental theorem of algebra. This is called fundamental theorem of arithmetic. That every non-zero integers, every non-zero integer every non-zero integer can be written uniquely as a product of prime number. And this is up to plus minus 1, right? So for example, minus 2 is minus 1 into 2. Or 2 equal to, you can write minus 1 into minus 2. Uh, so everything is, so this associate comes because it's up to up to a unit, like 15 equal to 3 into 5. You can also write it as minus 3. You can also write it as minus 5 into minus 3. And the ideal, so minus 3 is also a prime element, because the ideal gen by minus 3 is a prime ideal. So everything is defined up to units, up to associate. This decomposition holds, and this decomposition is unique. So this the example that Z is a UFD. So of course, here I have used that since Z is a PID, I have already proved in PID in any integral domain that the prime elements are irreducible, and in a PID, irreducible elements are primes. So product into irreducible for Z is equivalent to product into irreducible into prime numbers, and because we define an element to be uh, so there is always an ambiguity up to unit, so that is allowed. So up to ambiguity by unit, so there can be associate, we allow. Okay, so that's the definition of unique factorization. So in a UFD, one of the next proposition is in a UFD. So okay, Z is a UFD. What are the other examples of UFD? So we'll see very soon other examples of more examples of UFD. So let me do a couple of lemmas, then we'll see more examples of UFD. So in a UFD, every irreducible element is a prime. Okay. So how do you prove this? So that is the next lemma, that every irreducible is prime. So in a PID, we have seen every irreducible is prime. In UFD also every irreducible is prime. So let P be an irreducible element. If P divides AB, so suppose P divides AB, so P be an irreducible. So okay, so maybe I should say, so P is not equal to 0 and not a unit. Maybe I should say, just to be more cautious. So P is not equal to 0 and P is not a unit in A, and A is, we assume A is a UFD. Okay, so maybe I should be that P be an irreducible in A. Excuse me. Uh, in A UFD A. So P is not equal to 0 and P is not a unit in A. So now if P divides AB in A, so that means in particular I mean A and B are in A. So then AB equal to some lambda times P. Okay. Yes. So P divides AB, then uh, so P is not equal to 0 and P is not a unit in A. If uh, P is not equal to 0 and P is not a unit in A, and so assume that if P divides, so assume that, sorry, P divides AB in A, where A comma B is in A, then AB equal to some lambda times P for lambda in A. So then you see what happens here. You look at the both the sides. So AB equal to lambda times P, and P is a prime. So P is an irreducible. P is an irreducible in A, right? So note that P is an irreducible in A, as it is a prime, and every prime is an irreducible, right? Uh, and sorry, so sorry, yeah, sorry, no, P is an irreducible, right? So yeah, so P is an irreducible. So P is an irreducible. Now AB equal to lambda times P. So in one of the factorization of AB, you consider the element AB. In one of the factorization, this is a factorization. So AB can be factored into. So you have a factorization of lambda because it's a UFD. So AB can be written as some lambda has a factorization, and then after taking P, which is an irreducible, you get a factorization of AB, right? So AB has a unique factorization. Note that AB has a unique factorization in the ring A. And so if lambda has a factorization, you apply when the factorization of lambda, you get a factorization of AB, right? So in one of the factorization, P appears in the factorization, appears in the factorization. in the factorization. So that means by uniqueness of factorization, when I factorize A into something and B into something, P appears either in the factorization of A or in the factorization of B, right? Okay. So by uniqueness of either in the factorization of A or in the factorization of B. So thus P divides A or P divides B. This implies that P is a prime as required. Okay. So what did you do? So see, you look at this again. AB equal to lambda times P. So AB equal to lambda times P, and then you write as Q1, Q2, Qn into P, where lambda equal to Q1, Q2, Qn is the factorization of lambda. On the other hand, A you write R1 and 2 RS. These are factorization into irreducible, and B you write as a factorization of T1, T2, Tm. Then AB equal to R1 into RS and T1 into Tm. And AB is also equal to Q1, Q2, Qn into P, right? But these two factorizations are same. And what does the definition of UFD say? That these two factorization, both the factorization gives a factorization of the same element, so it is unique, so they are same. So P appears in here also in R1, R2, RS, T1, T2, Tm is equal to Q1, Q2, Qm, P, this set. So P is actually equal to one of the either R1, R2, RS, or T1, T2, Tm. If P is one of the T1, T2, Tm, then P divides B. And if P is one of the R1, R2, RS, then P divides A. So P divides A or P divides B. So that's what you record. You started with P is a reducible element which divides AB, and you concluded P either divides A or P divides B. So that is the definition of prime, right? So that is the explanation. So if something divides AB, then it divides A or it divides B for every reducible. So every reducible is prime. So in particular, we saw this example earlier. Z root minus 5 inside C. So here you had two different factorizations. So so Z is a UFD. We saw fundamental theorem of this thing, and now we saw that every irreducible is prime in a UFD. So here we saw 2 is a irreducible, which is not a prime. So we conclude that Z root minus 5. So non-example Z root minus 5 contains an irreducible 2, which is not a prime. So Z root minus 5 is an integral domain which is not a UFD. This is an example of a not a UFD. So every integral domain need not be a UFD. And next we create more example by proving that every PID is a UFD. Okay, next lemma is that every PID is a UFD. Okay, so we gave the definition of UFD, and then we saw example that fundamental theorem of arithmetic that Z is a UFD. Then we proved that every irreducible is prime in a UFD, and then we saw some integral domain Z root minus 5, which is not a UFD. Now we give another example of PIDs that PIDs are UFD. So every PID is a UFD. Okay, so uh, so so let's what do you have to do? You have to you take a non-zero non-unit R in a PID, then you have to prove that R is a product of irreducible. Okay, so so suppose uh, R is irreducible, then we are done. If not, R can be written as, so then R, if it is not irreducible, non-zero, non-unit, if it's not irreducible, then it is a product of irreducible. So let's say R equal to, this is reducible, so R equal to Q1 into Q2. If both Q1 and Q2 are right, so if R is not reducible by definition, so we run a PID, and suppose R is a non-zero, non-unit element, and suppose R is not reducible, that means R can be written as Q1, Q2, where Q1, Q2 are both non-units, right? That is the meaning of it is not being irreducible. If for every Q1, Q2, one of them turns out to be unit, that means R is irreducible. So we are done. So that was the case. So case one, this is case one. This is case two. In case two, it is Q1 into Q2. So then case one, if R is irreducible, then we are done. So now you do case two. It is Q1, Q2, and Q1, Q2 are both non-units. If Q1, Q2 are irreducible in sub case one, then done. Right? So you have a product into irreducible. Then we'll prove uniqueness later. Then we are done. First, I am expressing product into irreducible, and then I'll talk about uniqueness. So otherwise, you write Q. So let's say Q1. Q1 is not a irreducible, so then it's not a unit. So Q1 can be written as Q1 1 into Q1 2, right? And so you had the element R. R is a multiple of Q1, so R belongs to the ideal generated by Q1, and Q1 belongs to Q1 equal to Q1 1 times Q1 2. So R is contained in Q1 and Q1 is contained in Q1 1, and this can continue. So ultimately, you write Q1 1 as, if Q1 1 is irreducible, then we are done. If not, you write it as product of two elements. So this process continues, and ultimately we arrive at finitely many irreducibles, and so we have the product into irreducible. But the question is, how do you know this process stops, and how do you get irreducible? Can this go infinite number of times? And can you never get irreducible? All the time you write Q1 equal to Q1 1 in Q1 2. Next time you write Q1 1 equal to Q1 1 1, Q1 1 2, and Q1 2 write Q1 2 1 and Q1 2 2. And then Q1 1 1 again you write Q1 1 1 1 1 and Q1 1 1 1 2. The question is, do you arrive at irreducible or this continues infinitely? So we claim that this stops. Why? So suppose at some point we arrive at units, and that's when each of these chains stops. So otherwise you get R contained in Q1, Q1 contained in Q1 1, and maybe Q1 1 is contained in Q1 1 1, and like that. And I'm claiming that this stops at finitely many steps. So how do I prove that? Uh, so uh, so 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 you defined, let's say Qn is Q1 1 1 1 1 up to n times, and then you define union of this Qn. You take union of this, because this is an increasing chain. You check this is an ideal. Check this is an ideal. So any increasing chain, if you have I1 contain I2 contain I3 and like that, then union of In n greater equal to 1 is an ideal. In general, union of ideal need not be an ideal, but this is an ideal, because if x and y belongs here, then Rx plus R1x plus R2y also belongs to R1 for all R1, R2. Okay, so we show that this because suppose x and y belongs there, union of I, then x belongs to, let's say, I100, and y belongs to I200, then you take the maximum indices, then x plus y belongs there. Similarly, you pick any R, then Rx belongs to Im, let's say, and similarly R1x belongs to Im, and R2y belongs to Rn. Then you pick the maximum index, then R1x and R2y both belongs there. So their sum also belongs there. right? So it's easy to see that union of an increasing chain of ideals is increasing in the sense one is included in another. So with respect to increasing with respect to set theoretic inclusion, then their union is an ideal. So this is an ideal, and since it's a PID, it's generated by single element. Let's say Q, right? So then Q is an element of this union, right? So if it is an element of the union, then it belongs to one of them. Let's say Q belongs to Q and not. Because this is an ideal, this is principal. So it is generated by single element Q, as it's a PID. A is a PID. That's what is used here, right? So since A is a PID, we get this, that this is Q. And then Q belongs to the union belongs to, means it belongs to one of the member. Let's say Q and not. So anyway, Q and not, and this is the union, right? So Q, the ideal generated by Q is bigger than this. So that means, so then Q equal to Q and not, right? Ideal generated by Q equal to Q and not. And and so yeah, we had written it like this. Uh, so Q equal to Q and not. So Q equal to Q and not. So the chain stops at Q and not, right? So QM becomes Q and not, right? For all M greater than equal to M naught. So the chain stabilizes. So in particular, it means that Q1111 N naught times is same as Q1111 N naught plus 1 times, right? So they differ by a unit. So this chain stops at n naught level. So similarly, all these subsidiaries. So this is for the one we did. All of them will stop at a. Similarly, all of them will stop at a finite level. All of. So similarly, so arguing like this, arguing in a similar way, we get a factorization of R equal to Q1 into Qn into a product of irreducibles in A. So note that we have heavily used that A is a PID here. So where have we used? So first of all, R equal to if it's not irreducible, it's Q1, Q2. Here we have not used this PID. If they're irreducible, if R is irreducible, we are done. If each of them are irreducible, we are done. Otherwise, if one of them is a unit, another is so otherwise, if both of them are non-unit and not irreducible, then you break Q1 into this. Then this chain we got and you took the union. That is equal to a principal ideal. That is because it's a PID. So here PID is crucially used. Okay. So here it is used crucially. So and then this chain stops and it is a principal ideal that is also used. So the chain stops, and that is one property, but crucially, the chain is generated by single element. So then all these elements are associates, and the chain stops at n naught level. So similarly, all these chain stops, and ultimately you get a product into irreducibles. Okay. And what about uniqueness? So what about uniqueness? So suppose A equal to Q1 into Qn is a product of into irreducibles in a PID A for a non-zero non-unit element A. Okay, so then, but as A is a PID, so each QI is a prime, right? So irreducibles are prime in a PID. And so if you have A equal to some P1 into PS and equal to Q1 into Qn, then Q1 divides P1 into PS. So this implies Q1 divides, let's say, P1 for simplicity. But Q1 generates a maximal ideal. It's a non-zero prime, and so is P1 also a maximal ideal. And it divides. This means that P1 is contained in Q1. So this implies P1 equal to Q1 as an ideal. So it is implies P1 equal to lambda 1 times Q1. Lambda 1 belongs to A unit. So then you get so you cancel P1 from both sides. So you get if you like A mod P1, so you get P2 into PS equal to a unit times is a unit. So I can absorb it Q2 into Qn, and I can write this Q2 prime into Qn. So now we have by induction we have done. So next time I'll cancel Q2, and like all of these will be cancelled, and then the number of product of prime cannot be unit. So yeah, so by induction we'll get the uniqueness. Okay, so product into any prime is always unique. Okay, so the advantage, so for uniqueness also you use recipe ID, namely you use that every reducible is a prime element. And the prime elements generate maximal ideals. So if one prime divides another, then they have to be they have to be associates. Okay, so Pi and Qi have to be associates. So then you keep cancelling because the integral domain you can cancel from both sides. So then we get into lesser number of irreducibles, and by induction will be done. Okay, so we proved that every PID is a UFD. This proof is slightly involved, so you can think about it. Okay, so this chain argument is used, and it's a PID used multiple times. So then this is gives you a lot of examples, right? So then you get further example that uh, so you get further example that that examples fx is a UFD for a field. So now the question is, Z is a UFD. We have seen some integral domain which are not UFD. Then we saw every PID is a UFD. Is every UFD a PID, for example? Are the concepts same? So that's not true. So this is the new theorem we have. Next theorem that if A is a UFD, then AX is a UFD. Okay, and how do we prove it? So I'll not give the proof, but I'll say what is key result into this. But before that, I need to explain some uh, construction. I need to recall the construction of field of fraction of an integral domain. Okay, so let A be an integral domain. Then the field of fraction is like, so you have Z is an integral domain, and the field of fraction is Q, the quotient field or field of fraction is Q. So more generally, we can talk about this for field of fraction or quotient field, or the quotient field of an integral domain. So let A be an integral domain, and you consider F tilde is set of A comma B, where A is in A and B is in so A it's not A cross A cross A minus 0. It's Cartesian product of A and A minus 0. So you take all the elements on the first coordinate, second coordinate, you exclude 0. There's a set of tuple and define a relation on this f tilde, call it f tilde, let's say, that A is equivalent to B, if and only if. So you essentially think them as A by B. So in Z and Q, I gave the example, Q is like A by B, where A, B are integers, but also 4 by 6 is same as 2 by 3. So 4 by 6 is same as 2 by 3, and you define only A by B if B is not equal to 0. So you think them this as, so there is some identification, and you think this tuple A by A comma B as A by B. So more precisely, you define a relation that AB, this tuple is equivalent to CD if AD equal to BC. So again, if A by B equal to C by D. So this relation you can check, it is reflexive, it is symmetric, and it is transitive. So it is an equivalence relation. And you denote an equivalence class of AB in F tilde by A by B. Okay. And so F be the set of equivalence classes of F tilde. So now you change the collection. You find a new set F. F is the set of equivalence classes of F tilde. Okay. So so F is different from the set F tilde. Then elements of F look like A by B and C by D. And you define for A by B and C by D, you define A by B plus C by D equal to AD plus BC by BD, and AB times CD is AC divided by BD. Then you can see that with these operations, F becomes a field. And so, for example, 0 mod A will be the additive identity, 1 mod 1 or D mod D, which is equivalent to D by D, will be the multiplicative identity. A by B has multiplicative inverse B by A has multiplicative inverse B by A, multiplicative inverse B by A if A is not equal to 0, and additive inverse. And okay, so maybe I should first say about additive inverse as additive inverse minus A by B, and further if A is not equal to 0, multiplicative inverse B by A. So note that when you are writing A by B, automatically B is not equal to 0, because we have started with this tuple AB where A can be any thing in A, but B 0 is excluded. Just keep the example of Z in mind if you are seeing this for the first time. So Q, as I said, is A by B, where B cannot be 0. Okay, so Z cross Z minus 0. And so with these operations, this becomes a field, and we have an injective ring homomorphism from A to F by sending, so you can easily check that this is a field, and we have an injective ring homomorphism from A to F by sending A to A mod 1. Okay. And this is the smallest field containing A, in which every element of A minus 0 becomes a unit. More precisely, if I A to F be the injective ring homomorphism sending A to A mod 1, then for so we call this ring homomorphism, so Z is included in Q, right? You identify integers. If you write them in the rational number form, then you say that M is M mod 1. So that's what it's saying. Then you can check this ring homomorphism is injective, because if A mod 1 equal to 0, so you have to just check its kernel. So ring homomorphism is more or less clear, and you have to check the kernel. But if M1 equal to 0, 0 mod 1 is the identity, then that means A equal to 0, right? So this ring homomorphism is really injective. You can check, and this is the, so this is a field. In some sense, we can say this is a field containing this ring, and this is the smallest field. So in some sense, the definition is the smallest field containing this integral domain, and it is smallest in the following sense. You can make it more precise, that if you have any ring homomorphism phi to to any field. Okay, so if you have a ring homomorphism from Z to any field, then it will factor through. So it will induce field homomorphism in Q to that field, which will be which will match with the ring homomorphism you had from Z to that field. So more precisely here, if you have any injective ring homomorphism capital phi from A to K to a field K, then there is a unique ring homomorphism from F to K such that this diagram commutes. That means if you have any ring homomorphism from any A to any field which is injective, capital Phi, any injective ring homomorphism, capital Phi, then there will be a ring homomorphism from F to K, which such that if you restrict it to A, so this diagram commutes. If you start with A and you go phi, A goes A by 1, and then you have this, there is a unique ring homomorphism. So this is unique. This is unique. Okay, so this is unique ring homomorphism. So from F to K, such that if you go to A mod 1 and you apply this unique ring homomorphism, where you arrive is the same as you had originally gone by phi. Here injectivity is important. Otherwise, it will not be true. So, for example, from Z, if you take A equal to Z, there is a field Z mod PZ, and A has a ring homomorphism from Z to Z mod PZ. But if you take F equal to Q, then there is no such diagram like this. Okay, so injectivity is important. So this is called some property which determines this, but so there is a unique ring homomorphism which matches when restricted to A, so to speak. Okay, so this is the smallest field. Basically, informally, you can say if any field contains this, then it will contain the quotient field. Okay, so that's the definition of field of fraction. So why did I talk about field of fraction suddenly? Well, because I want to prove this theorem. So we are discussing example of UFD, and so remember in this course we are interested in ring of integers of quadratic field, and it will be important. This field of fraction will be important. Field of fraction will be UFD will be important. What is UFD and PID and their relation is important for us. So we are seeing example of UFD, and in this case, if A is a UFD, then one of the theorem is that AX is also UFD. So if A is a UFD, then the polynomial ring in one variable over A is also UFD. Okay, and in fact, what is easy to see, if polynomial ring over X is a UFD, then A is also UFD. That is not difficult to see. You can take that as an exercise. So I will not give a proof of this theorem, but what I will discuss is how do you prove this theorem. So the key to prove this theorem is what is called a Gauss lemma. So I will discuss it. I'll start from there next time, and we'll complete the proof. So then we'll generate more example of UFD, and it will be more clear to us what is the relations. In some sense, where do we stand? All this. So various classes of ring we learned: UFD, PID, integral domain, field, commutative rings. So we'll see the more or less the complete picture now. And as I said, our goal in the later part is to understand this ring of integers of quadratic field. We'll define what they are, and there this concept of UFD and PID will be very useful and important to us. Thank you.